So, could we terraform the moon? It seems a crazy idea, but it's a possibility. Our moon is right next door and our closest neighbour in space. However, it sits at the bottom of a gravity well, which means that spacecraft will require a lot of fuel to land and take off, as getting to the surface of the moon from low Earth orbit and back would need a velocity change of 6 kilometres a second, which is 3.7 miles per second. However, the moon has real estate and lots of it very close to Earth. Thus, the objective may be to get to the moon because of its proximity rather than resources or as a stepping stone and a stopping off point en route to anywhere else. Firstly, if we look at the resources, the moon is very poor in some of the elements that we need to survive, such as carbon, nitrogen, and hydrogen. There is oxygen, but it's tightly bound in combination with other elements. It can be extracted, but it requires high temperatures to get it out. There are metals, principally titanium, which have been implanted into ilmenite by asteroids, comets, and solar wind. Most of the other metals have sunk into the moon's core. It is possible that mining resources might exist on the moon, for example, potassium, rare earth elements, and phosphorus in a rock called creep, KREP. There are also sources of iron, magnesium, and calcium. However, the moon's principal resource is likely to be water ice in deep, cold craters close to the poles. Mined regolith could then be moved with lightweight buckets pulled by cables, rather like cable cars or ski lifts on Earth. These cable-based transportation systems could be useful ways to transport heavy loads around a site. This would avoid the need for roads for wheeled vehicles, which would kick up a lot of dust, which is nasty stuff. We'll talk about that in a moment. Are there any other ways to get between the moon's surface and lunar orbit? Linear motors or mass drivers could be used to propel buckets full of regolith into lunar orbit. Alternative electrical catapults could be used to put material into lunar orbit. Another device which would get mass into orbit is a space elevator or a skyhook. This would use an asteroid in geosynchronous orbit about the moon with a long cable reaching to the surface and another into space in the opposite direction. When the system had been proved to be stable, elevators could ascend and descend to get people and goods into space or back to the lunar surface. Another idea is the non-synchronous skyhook, which would include a cargo line which would revolve around the anchor asteroid, touching down synchronously at the same point on the moon's surface during each asteroid or lunar rotation. It would be like a giant starfish going around the moon. Cargo could then be hooked on at the ground to be pulled back into space. If the asteroid rotated twice in each moon rotation, the cable would touch down at two separate points on opposite sides of the moon. More frequent starfish-like combinations could be used to touch down at multiple points around the moon or on the moon's surface. These ideas also dispense with the elevators suggested for static skyhook systems in favour of rotating stars or Ferris wheels. If the cargo were released by the cable while it was ascending, it would be thrown into deep space with considerable force. This would mean that cargo and people could be transported effortlessly out of a planet or the moon's gravity well. So the fuel requirement of getting to the moon's surface or back might not necessarily be a complete deal breaker. Bases. Let's talk about bases. The lunar base. Radiation will be a big health issue, but a covering of lunar regolith would provide sufficient protection. A 20-ton lunar base would need to be covered with between 100 and 500 tons of regolith shielding. Alternatively, bases could be underground or protected by a 10-centimetre thick, that's 4 inches, glass domes to shield the occupants against solar flares and cosmic radiation. The moon experiences solar flares and extreme temperature variations, and temperatures are only stable in polar craters. For example, the Shackleton crater near the South Pole is 2 kilometres, 1.2 miles deep, so it may be a good place to site a moon base, along with parts of the 8-kilometre, 5-mile deep South Pole Aitken Basin as well. In fact, the poles would be the best places for bases because they have permanently shadowed craters with water ice and constantly illuminated highlands where solar energy could be collected. Together, this means that rocket propellant and fuel for lunar excursion vehicles could be manufactured from local water and solar energy collected in the highlands and beamed to the base using radio waves. Mining robots would provide a level surface upon which construction robots would then build the structure. Habitation and power supply modules would need to be delivered before human crews arrived. Further deliveries would include rovers, excavators, tractors, unloading and construction equipment, pilot-scale mining and smelting equipment, kilns for metallurgy, telescopes for astronomy, medical labs and other scientific modules, and more habitation modules. Inflatables are made from quilted pillow-shaped components which contain fiber composites. They have been used as habitation modules in space. They would be inflated rather than being built and would use a regolith layer to protect the occupants from radiation. Some proposals feature foam-filled fabrics which would be injected while the structure is being pressurized. One difficulty with these structures is that the interior floors would need to be filled with a compacted regolith, while beams and struts would also be required to stabilize and enable them to cope with the weight of the regolith over the top. Finally, internal elements would need to be constructed without introducing lunar dust, which is likely to be very difficult. Structures built from concrete and lunar regolith would use local materials where possible. Regolith could be confined by fabrics and films and built into structures using ancient techniques from Earth to make arches and walls. It is possible to heat regolith in microwave ovens to temperatures at which it will fuse into rock-hard ceramic bricks. Some proposals recommend the use of lava tubes as bases. They would have stable temperatures and be protected from radiation. However, lava tubes are probably not easy or safe places to do construction or building work, and so are likely to be overlooked until the first colonies are running successfully. Each astronaut will require about 34.4 square meters, that's 370 square feet of floor space, and a ceiling of 4 meters, that's about 13.1 feet. The high ceiling is due to the moon's weak gravity, which causes people to lift off the ground when they try to walk or run. This makes it possible to calculate the dimensions of a moon base using the number of astronauts and the amount of equipment needed at a starting point. Let's talk about dust now. The moon's gravity makes it hard to excavate with the same kind of equipment that we use on Earth. Therefore, cutting, scooping and moving regolith will be problematic unless large masses were used to hold down the equipment. One alternative is to blast the regolith out with explosives, which, if the charges are placed deeply enough, can fragment it without creating too much dust. Apart from being sticky, lunar dust is extremely abrasive and electrically charged, so it could damage equipment and harm people. Estimates say that 50% of the regolith has particle size smaller than fine sand, and approximately 20% is smaller than dusty. Lunar dust is known to cause vision impairment, instrument inaccuracies, machinery breakdown, traction loss, abrasion, thermal control issues, seal failures, and inhalation issues. Basically, it's nasty stuff and best avoided. In mining sites on Earth, dust is suppressed by spraying it with water. However, water will be such a precious resource on the moon that it's unlikely to be wasted in this way. Debris from any impact or explosion can travel a very long way in a vacuum on the moon, for example, before gravity brings it back to the surface. Firing a rocket from the surface could cause dust and debris to travel halfway around the moon. Lunar dust might be used as a resource, for example, to create bricks or fill sacks, or for spraying onto habitation modules. This could provide radiation protection and flexible structural integrity using local materials. However, high temperatures may be needed to turn the dust into solid material. The lessons learned from this research would aid in the construction of larger moon bases, as well as in the design and development of a Mars base. However, the experts say that there are significant differences between Moon and Mars. Mars has a thin atmosphere, seasons, and a different type of dust, and twice the gravity of the Moon. They add that lunar conditions provide a more rigorous environment for thorough testing than Earth. Let's get on to talk about terraforming. Lunar bases could be expanded into a shell world in which a spherical shell could be constructed right around the moon, within which Earth-like conditions would be maintained. This might be started by joining up the domes so they interconnect, and then gradually expanding it until it covered the whole of the moon's surface, or creating a completely new shell around the whole of the moon. This shell would protect the occupants from radiation, maintain comfortable temperatures and air pressures, and provide artificial lighting. It could dehumidify the air and let the collected water fall as rain. People are liable to look askance at anyone who suggests that the moons might be terraformed. From a common sense point of view, it seems completely impossible to fix our moon so that we could live there without a protective dome or shell. But two inconvenient truths get in the way of this logic. They are the Saturn's moon Titan, which has a 600-kilometre deep, that's 373-mile deep atmosphere, and Neptune's moon Triton with its 800-kilometre thin, 497-mile atmosphere. But is the moon big enough to retain an atmosphere? To answer this question, it's worth looking at the diameters of the three moons. Titan is 5,150, Triton is 2,700, and the moon is 3,474 kilometers across. So that means that our moon is somewhere between the other two when it comes to size and mass. The surface pressures are Titan has a surface pressure of 1.5 atmospheres, Triton 0.0014, and the moon 0, of course. However, there are big differences in temperature and the distance from the Sun. Triton and its planet Neptune are 30.1 astronomical units from the Sun. An astronomical unit is the distance between the Earth and the Sun. Titan and its planet Saturn are 9.6, and our moon is 1 astronomical unit. This means that our moon would get a great deal more solar radiation than the other two, which may excite atoms in its atmosphere and allow them to escape from the moon's gravity faster than on the other two moons. Therefore, the moon is unlikely to hold an atmosphere for millions of years, as it would be blown away by the solar wind. But thousands of years should not be a problem for a base and somewhere where we could go en route to anywhere else. The moon's 1/6 gravity would need 6 times the atmospheric mass per unit area when compared with Earth, which means that the mass of volatiles needed on the moon would be about 1/3 the mass of Earth's atmosphere. This is roughly the volume of a 60-kilometre, 37-mile sphere of water, which could be supplied by a single medium-sized asteroid. Let's talk about days on the moon. Another problem for the moon base is that both days and nights last a full 2 weeks, that's 336 hours each, which would require plants to be grown under artificial light. This would be expensive in power and monetary terms. If this is not corrected with artificial lights and shades, a longer-term solution would be needed. The moon could be spun up using impacting volatile-rich asteroids. However, the moon is not perfectly spherical and has a slight tidal bulge facing Earth. Therefore, a spinning moon would be affected by Earth's gravitational pull, which would generate a torque that would eventually bring the moon back to tidal locking with the same side always facing Earth. Any giant impacts, either to introduce volatiles or to spin up the moon, would cause debris from any impact or explosion to travel a very long way in a vacuum before gravity brings it back to the surface. Therefore, a major impact could put debris into the moon, into its orbit around the moon for a very long period, as well as causing damage to equipment and facilities. The solution to both radiation and day length may be to build a shell world around the whole of the moon. The underside of this could be used to project the sun and stars and simulate days and nights, and the shell could protect the surface against radiation. This is probably the best long-term solution, and would allow the moon's climate and living conditions to be controlled. And it would not fix mineral, but it would not fix the mineral deficiencies though, and carbon, nitrogen, and hydrogen would still need to be brought from somewhere else. So it is possible that our descendants might terraform the moon, but it's going to be very hard and that'll take a long time. So I don't imagine it will happen for many thousands of years, but I think it might. Anyway, thanks for watching. Bye.